So I have a mass on the end of a very light string. The string is a length L long, and it's affixed to a point right here. I'm going to release this pendulum so that it swings downwards. All right, everybody understand the dynamics of the question? I'm going to be asking about points A and points B. What is the acceleration at A just after it's released? B, how fast is it moving at point B? And C, what is the tension in the string? At point B. You should be able to do this. Can you? Prove it. This is all last semester. So all you people got A's and B's. You should be able to do this, no trouble. You earned those A's and B's, right? I'd argue that probably the first question might be the one that threw you for the biggest loop. But when you release it, the only force acting on it is gravity straight down. So acceleration is just going to be G. That one's a little, just kind of a, I don't know, a trick. But you'll understand why I asked it in just a minute. Does the mass change height? So I think the pathway to finding out how fast it's going is probably conservation of energy. And I'm hoping that that's not a big surprise, because this problem is in your notes. If you look back, you'll find it. So as it swings downwards, it converts its gravitational potential energy into kinetic energy. That's it. Again, I'm not trying to insult you if you didn't know it was that easy, but I just noticed that the bob made an obvious change in its height. So conservation of energy seemed like the best way to go. Cancel the m's. V is going to be equal to the square root of 2gl. When it makes to the bottom, there's two forces acting on it, tension upwards and weight downwards. I also notice it's traveling in circular motion. So I'm thinking net force equals MAC. So if you said net force equals 0, no, it has to pull up more because it's traveling in a circular path. So that would be tension minus mg equals mv squared over L. The radius of curvature is L. And this is velocity. So a couple of substitutions. And we're done. So I see tension equals 3mg. And again, this problem is in your notes. You look back far enough, you should find it. I'm not trying to insult you, though. Just throwing out there that this is the start of the question. I should be able to expect you to do this on tomorrow's test, or I'm sorry, on Friday's test. It's old, but it's content we've had. Nothing of this is new. Now, I hope you understand that that was just so I have a place to begin. What if instead I have a rod that I fasten to the wall at a point here so that it can pivot, and I release it so that it can swing downwards. To look like that. I would just ask the same questions, like, what is the angular acceleration the moment it's released? I like that question. It's a solid one. Maybe B, how fast is it going when it makes it to the lowest point? Or C, what force does the pivot have to provide to keep the meter stick from falling when it makes it to B? Same three questions. I think you should be able to do this problem. I'm saying that knowing that that's highly unlikely, but with the information we've had in class, I think you should be able to extrapolate to this. And again, I don't believe that there's anything beyond what we learned in the last week, and maybe a little bit of last week, that's needed for additional content here. But I think that if I gave you this test, I would have a lot of disappointed people. Disappointed in me and disappointed in themselves. But I have to have you understand something. I'm counting on you remembering first semester. So let's start at the beginning. When I release it at A, there are two forces acting on it. There's a force upwards here at the pivot. There's also a force downwards here at the center of mass. Those are the two forces acting on it when it's first released. However, only one of these causes a torque. This one does not. It acts to pivot, so the torque arm length is 0. This one, on the other hand, acts at the center of mass. So let's say that this is a object of mass m, length L. That way it's exactly the same as the variables we just used. So the torque has 3 components to it. There's R, F, and the sine of the angle. I know, this is just yesterday, so I'll be patient. The one I should expect the least from you. R is the distance from the pivot to where the center of mass is. That's going to be L over 2. F is the weight, mg. By looks of it, sine of 90 degrees. You have to build a torque. So it takes a little more work to build a torque, but we've done it. That's just going to be LMG over 2. Is this balanced or unbalanced? If I let it go, will it just hang there in space, or will it rotate? I believe it's unbalanced. I believe there's only one torque that acts, and therefore it's unbalanced. So that has to equal I alpha. Newton's second law. Again, torque requires more steps. I'm going to have to figure out what I is for a rod rotated about its length. You can look it up in a chart, or if you have it in your notes, you can look it up in your notes. Or if you have it memorized, you can have it memorized. I have it memorized. Cancel the M's, cancel an L, and I get that alpha equals 3G over 2L. Any question about that? Yes, sir. Say again? This is a long rod rotated about one end. So I just looked it up in the book. A rod about its end is 1/3 ml squared. We also did the calculus on this a couple days ago, but I'm not sure if you were here or not. A rod about its middle is 1/12 ml squared, but we'd have to look it up in the chart. I am not expecting you guys to have moments of inertia memorized for tomorrow's test, but I might have them on a chart on, not tomorrow's test, Friday's test, but there might be a chart. Maybe we could look them up at least on a chart, but that's not the case. I mean, I'm not trying to have those memorized, have you have them memorized at this point. I think it's good for you to have the disc, the ring, the rod, and the spheres memorized because they show up a lot, especially the disc and ring. Interesting. This is a side question that's not asked. Is there any time when is there a point on the meter stick where the acceleration is G? I think there is. It doesn't look like it. I mean, if you look at that, that might not tell you, but remember, A equals alpha times R. G equals 3G over 2L times R. If I solve this for R, it will tell me where on the meter stick the linear acceleration is G. G's cancel out, and I get that at 2/3 the length of the meter stick, the acceleration is G. That means everything past that is accelerating faster than G. Now, you wouldn't see this in a meter stick, but if you release other long objects, they bend because they're being asked to accelerate faster than gravity is pulling them downwards. Towers break when they're knocked over. Cranes flex when they fall over. It's all because of that. I probably wouldn't ask that on a test, not now. I just thought it was an interesting aside. So let's stay on task. So for those of you who are getting more and more concerned, I don't need this again, so I'm going to erase it. I wanted the velocity when it swings through the lowest point. Does the object here have gravitational potential energy? Is its mass above the lowest point it's going to attain? I believe so. Is it a stretch for you to realize we're talking about the center of mass here, often called the center of gravity, like I said first semester? So we're tracking how far the center of gravity moves. I think the lowest point is when the center of gravity is L over 2. So I think this problem will have mgh here, and we'll have 1/2 I omega squared here. Same thing as before, conservation of energy. But a twist. The change in height isn't the whole length, it's L over 2, because that's where the center of mass goes. And that's going to equal 1/2 I omega squared. Just using I all the time, not the mass. I think you guys could probably work that out and find an expression for omega squared. Lots to cancel out though, right? So is it 3G over L? That's what I get. Again, I know you weren't expecting this, but none of this is new. Well, maybe some of it is. Is the object traveling in circular motion as it passes through point B? I think the center of mass is experiencing two forces. Center of mass is experiencing a force upwards, tension or something, I don't know what you even call it. And the center of mass is experiencing mg downwards, but the object is rotating through point B. So I think net force is going to equal m omega squared times r. This question might be a stretch. First two, no trouble with me given, but this one might be a stretch. That's going to be tension minus mg. I remember the other version of centripetal acceleration. It's omega squared times r. It's on the equation sheet. But, and keep this in mind, although I have m and I have an expression for omega squared, what do you think r is in this case? I'm not sure you guys would know this. There's no reason to, but we still focus on the center of mass. So that would be the distance from the pivot point to the center of mass. I think that's a stretch. I'm not sure you would have known that without me helping. There'd be no reason for you to. But you can battle all that out, and you get that T is going to be equal to 5/2 mg, which, by the way, is slightly less than the ball on the string, which doesn't surprise me. It shouldn't have to pull up as hard. The weight isn't as far away. Some of it's not moving as fast. So, all right. That's the first 15 minutes. 17, you're going to be calculating the moment of inertia of the door. And it's trying to, I'm trying to get you to see something here, that you treat the door as a rod. It doesn't matter that it's a huge slab. You treat it as a rod anyways. And the reason is because think of the middle of the door. A piece of mass here along the middle of the door is the same distance away from the hinge as a piece of mass here on the middle of the door. Moment of inertia isn't about how long the door is this way, but how wide the door is this way. It's about how far away each piece of mass is from the moment of inertia. So I just need to know how wide the door is and how heavy the door is, and that's it. I can treat it just like a rod. So for the first question, it's just 1/3 ml squared, and for L it's 91 centimeters, and mass is 25 kilograms. Then, though, they move the pivot to be 15 centimeters in from the edge. So these are the stupid doors at Dillard's. You know what I'm talking about? It's where they turn. I guess that makes them way cool. But I just think they look distracting. I just want them to part, like, like curtains for me to enter, like I'm going on stage. I don't like that whole flexing in the middle thing. You could redo the work we did in class. Set your limits from this point to this point. which from here would be 15 centimeters this way and 76 centimeters that way, and do the integral. You'd have to remember the integral that we set up to do this. I don't want to do that if we can avoid it, but we could. But I introduced something yesterday that or maybe last week, that would probably make this easier. It's called the parallel axis theorem. And the parallel axis theorem is the reason I assigned this problem, to remind you that you can use the parallel axis theorem to move the axis to a different location on an object if you already know the moment of inertia through the center. And we do. On the chart, the moment of inertia of a rod through its center is 1/12 ml squared. In some classes, we even showed this yesterday, but I don't know if it was this one or not. Now, once I know the center of mass, once I know the moment of inertia at the center of mass, I want to shift it. But I have to know how far I'm shifting it. So the center is here, and the whole thing is 91. This must be 30.5. Right? The midpoint would be 45.5. So I think that's got to be 30.5. Is that good? So if I want the parallel axis, it would be 1/12 m times 91 squared plus m times 30.5 squared. This would be the moment of inertia about this parallel axis. Okay, this is 17. Is that okay, or do we need more follow-up? Next question? Yes, sir. Number 11. I have three 200-gram masses in a equilateral triangle. What is the triangle's moment of inertia about the axis to the center, and what is the triangle's kinetic energy if it rotates about the axis at 5 revolutions per second? So does that look equilateral enough for all of us? They give us lots of measurements. So the one measurement they don't give us is that distance, which we need. But they tell us that the side length is 20 centimeters, I believe, 40 centimeters. That means that this triangle right here has a side here that's 40 and an angle of 30 degrees. I believe we can figure out R from this. Yes, sir? 20, half of it. 20. I still think we can figure out R from this. Cosine 30 equals 20 over R. So R is 20 divided by cosine 30. Start there. Now, moment of inertia for point masses, just this. So once we know that, would you guys agree with me that each mass is the same value? They're all 200 grams. Would you also agree that each mass is the same distance from the axis of rotation? So I'm going to have 200 times 20 divided by cosine 30 squared times 3. That's the moment of inertia. Probably should put it in kilograms and meters. probably. Mostly because they're going to ask for the kinetic energy in a minute, and that's probably in joules, or should be. All right, set that aside a minute. The kinetic energy of the system is 1/2 I omega squared. Be careful, they give omega in revolutions per second. And whenever you're going to use an angular quantity to calculate something, it's got to be in radians per second. So before I do that, I need to multiply by 2 pi to get radians per second. So 31.4 radians per second. So now I think I have all the things necessary to figure out the kinetic energy. And this will be in joules. Torque has 3 parts: torque arm, force, and the angle associated between those two. Here the torque arm is, I should probably put this in meters. So I'll divide by 100. The force is 150 because it's mg. And clearly sine of 90 degrees. This might not be obvious to you, but all strings come off pulleys tangent to the pulley. Did you understand what I just said? No matter how you try to pull a string off of a pulley, it has to come off the pulley tangent to that pulley, which means that whenever a string is applying a torque, it does so at an angle of 90 degrees. It's always tangent to the pulley. So whenever there's a torque with a pulley involved and the string is around the outside of the pulley, the angles are going to be 90. All right, we've got a 10 kilogram mass. I believe it's negative. Just from looking at it, it's got to be in the opposite direction. But we can prove it. Torque arm length is this way. Force is downwards. My thumb points into the board. That's a rotational direction into the board. If out of the board is positive, then into the board has to be negative. I'm going to intentionally put a negative sign here to remind myself of that. Your book does this different. Look at the way the book does it. If you like the books better, do it that way. But I'm going to do it that way. Again, 22.5. I'm going to convert to 0.225, put it in meters. And it has a force of 100, sine of 90 degrees. And now for the third torque, the one some of you probably forgot. But the wheel has a mass of 5 kilograms. We are no longer at the center of mass of the wheel, so there is a force this way of 50 newtons. So there's the torque from the center of mass of the wheel. This torque is also negative. It acts 7.5 centimeters away from the edge with a force of 50 newtons. And as long as the wheel is being released so that the center is horizontal, then that is also a sine of 90 degrees. So there are 3 torques that act in this system. What?
Would the center of mass be 15 centimeters away since it's in the middle?
No.
So why would it be 7.5 centimeters?
I think the center of mass is going to be at the middle of the wheel. Wouldn't you think so?
Yeah.
This distance is 15.
Yeah.
I'm going from here to where the center of mass is.
Oh, so okay. I didn't realize that you would like subtract those. I thought you would just do the 15.
I'm not really subtracting. I need this distance, which has got to be the other 7.5 centimeters.
Okay, is it pivot from that?
You guys follow that argument okay? So I did not make that clear. I just made an assumption. All right, so net torque. You can add all those up. You guys can do arithmetic. I don't feel as though I want to do arithmetic. Is that okay? So you guys get the number? I don't really know what direction it rotates, but I'm thinking it rotates in the negative direction. It looks like it. That 10 is hung pretty far away. If it were me and I were writing this problem, there would probably be another step. I'd probably want to know the acceleration of the system. I'd probably ask an intermediate question, like what is the moment of inertia of the disk about the new axis, requiring you to use the parallel axis formula for the disk. I'm sure of it. I'm sure I wouldn't miss this opportunity. So I'm thinking that I'd probably do that. I might be nice on a test and say, use the parallel axis theorem to find the moment of inertia of a disk about the new axis. But then having you set that equal to I alpha and finding the acceleration. Yeah. Oh, yeah. The only difference between probably what would be on the test and what this problem is I probably would make this M, this 2M, and this 3M. And I'd probably make the radius R. That's probably the only difference, because that's how the AP exam would probably do it. But it's the same thing. But yeah, I probably wouldn't go any further than this, although you do realize that this problem could be the problem we had at the beginning of class 2, right? With the ruler kind of going downwards. You could find how fast it's going and stuff. But that's actually a very hard question because these guys change height and it's not obvious how much height they change. So I wouldn't ask that question of you guys. Maybe without the two masses hanging on there, sure. But with the two masses, not so much. I think that makes it really hard. All right, that was fun for me. Probably not for you. Anything else in the homework you'd like me to speak to? There's 2 minutes. All right. My plan tomorrow